Okay, this is a brief tutorial on work and power and potential kinetic energy and that kind of thing. So let's look at a work and power example. Let's say we apply a diagonal force where 30 newtons of that ends up being vertical, 40 ends up being horizontal. What we're going to find is that since the box only moves horizontally, the 4 meters, this 40 Newton force is the only component of the force that actually does any work, and you're applying it over the distance of 4 meters. So let's look at a couple of questions related to that. So we want to know what the work's done by the horizontal component of the force. So just like we were saying, for A, work equals force times distance. So work equals the 40 Newton horizontal force times the distance of 4 meters. Remembering that from our diagram, this is the only component of the force going horizontal. So we take 40 and multiply it by 4, you get 160 newtons times meters, and newton times meter is a joule, so 160 joules of energy. B, what is the work component done by the vertical component of the force? Well, the vertical component of the force was 30 newtons, but it doesn't move vertically, so if the distance is 0, it's not moving that direction, so the work equals 0 joules. It doesn't do any work in that direction. So total work done is just going to be the 160 joules done in the horizontal direction. What's the power? Power is how fast you're doing work. So power is work divided by time. So it's how fast. So it's 160 joules divided by the 10-second time. That's 10 seconds. So we get 16 joules divided by seconds, which would be 16 watts. Often abbreviated by a W. So that is our first problem. Let's say if we start from rest, we move a 100-kilogram crate by applying a net force of 50 newtons for 4 seconds. It results in a final speed of 2 meters per second if the crate moves a distance of 4 meters. What's the work? So for applying 50 newtons of force, 4 meters. So our work is just force times distance. We'll assume all that force is applying horizontally now instead of being at an angle. So we got 50 newtons moving 4 meters. So 50 times 4 would be 200 Newton meters or 200 joules. B, we want the kinetic energy. Kinetic energy is 1/2 mv squared. So it's going to be 1/2 100 kilograms. Remember, masses have to be in kilograms times the velocity of 2 meters per second squared. So 0.5 times 100 times 2 squared is also 200 joules. So if the kinetic the work applied should be equal to the kinetic energy if it's all working in the same direction. And then the power in this case will be work divided by time. So it'll be the 200 joules divided by, in this case, 4 seconds. So 200 divided by 4 is 50 joules per second, or 50 watts. And so that would be your answer there. That's the same problem, so we'll move on along. So if a crate has, now if we do potential energy, it's all based on how high we lift the mass. So we got lifted 2 meters above ground level. So potential energy is mgh, where g is our acceleration due to gravity. That means we have the box, and it is above a surface by some height h. So if we plug in potential energy is equal to 100 kilograms times, we'll use the rounded off value of 10 meters per second squared, times the height of 2 meters. So the potential energy will be 100 times 10 times 2, or 2,000. Now what's the unit? A kilogram meter per second squared is a newton. That's a meter, so that's the equivalent of a newton meter, so you still get joules for a unit. All right, that's been a brief tutorial of work, and power, and kinetic energy, and potential energy.